Now, of course, as any deep tech startup, the heart and soul of the company is what happens on the technology side. And today, we have our CTO, Dr. Marco von der Leyen, to give you an idea of what we have done so far and what we are looking to do ahead. So at this point, I'd like to give the floor to Marco and let him present.
Thank you very much. It's a great pleasure to talk to you guys about the work that the tech team has been doing over the last couple of months, some of which I think is very exciting and some of which you've already seen during the lunch break. So let's get started with a question that drives our, I guess, daily work, which is why? Why do we work on this, and why do we work on quantum random number generators, and what is the purpose of that? Why would someone care? And I think it's a very, very fundamental question, specifically around the topic like quantum random number generators, but quantum is the existential part. It's something that's used a lot by many people. It's very difficult to understand, even for me. I think it's something that's non-intuitive, but it comes up in conversations more and more. And the thing that people should care about, in my opinion, is what is its usefulness. So not all QNGs are created equally. There's many providers of quantum random number generators that actually do have, well, some don't, but some do have a quantum source. So the process by which the random numbers are generated is due to a quantum process. However, what does that mean for me as an end user? A quantum process is a microscopic process which happens on the smallest scales, but I use macroscopic devices, right? I don't use quantum processes in my devices. I use an electronic device that gives me a result of some quantum measurement. So if I don't have this, assurance in the connectivity between those two microscopic to macroscopic translations, it's kind of pointless to have a quantum random number generator. So I really need to focus on leveraging the quantum aspect of the random number generators, otherwise there's no point in doing it. Now, one feature that these three products in our product family for cybersecurity have in common, and here we have the Apex device, which goes to a couple of gigabits per second, the Vertex PCIe card, and the newest addition to a family, which is the system on module, which is here depicted with the evaluation board. They all have disk. So they're all built around this very fundamental technology that we've developed many years ago. And I want to illustrate, give an example for why that matters. So many of you will have not seen this. This is the quantum chip that sits on the system on module, and that powers, or gives the quantum functionality that sits behind our products. Now, this is just an illustrative example. This is not how someone would attack it. Possibly they would, but if I were to send electromagnetic radiation of some sort through that chip, you can see it passing through, there will be components, which I've highlighted on the right-hand side, that will be affected by that. Momentarily, for a short amount of time, could be continuously, we don't know, right? There's some sort of modification, external penetration of our system that our system will have to react to. Now, on the right-hand side, you kind of see a schematic. You have a laser, you have a first beam splitter, which going south, you have a certification photodetector, and then the entropy part, which comes on the right-hand side. So it's a very simple circuit. It has an optical source. It doesn't actually matter in our system what that optical source is. It can be anything. You have a certification channel and an entropy channel. And that is as fundamental as it sounds. It's the basis of all of the technology that we do at Quantum-Nice. And I'll explain why this is very essential in a second. So if you have these electromagnetic pulses that go through, you might expect a signal that looks like this. The blue stuff is just the random numbers, right? Over time, you get some signal. It looks like, if I were to integrate this, I would get some sort of Gaussian distribution. However, you see in the certification channel that there's a drop, a short drop in the entropy value, which you wouldn't detect just by looking at the blue signal if you were to average over the entire system. If you just look at the distribution for this very small amount of time, firstly, the numbers that are being generated are not enough such that the statistical test would make sense, broadly speaking. But even if that was the case, you can average it and it will be passed as a cryptographically secure random number generator or sequence. That's a problem, right? Because if I only look at that very short moment when I have low entropy, and I know because I induced that failure, I cannot trust my random keys or entropy. So this is the distribution that I just talked about. On the left-hand side, it's just a short sample without any distortion. On the right-hand side, it is a short sample, equal time, with 10% distortion. That means I've reduced the entropy that has been generated in 10% of the time that I've been letting it run. You can see that the values on the right-hand side are much higher, so it's much easier for me, the guess, but more than 50% easier, for me to guess what that value is. And by the way, I didn't switch it off, I just slightly reduced that entropy value, and it has given me a much higher chance of guessing what the correct value is that ends up in my cryptographic keys. Obviously, there's hashing procedures, and etc. We can go into many nuances, but generally, this is the concept. That means our disk protocol allows us to have instantaneous knowledge of randomness. I don't want to overload you with too many plots, but I think this one is quite important. What I've done here, I've just plotted two distributions that are very slightly different in the sense that the distribution has a different sigma value. So the standard deviation is slightly changed from 15 to 13. I picked a random value at 90% of the integral, and you can see that there's a significant difference, and that would not be picked up by any system if you do not have the disk protocol. Why is that important? Firstly, it prevents the presence of low entropy strings in cryptographic use, which leads us to the Spark system. On the top right, you can see the relative size of the chip compared to the, here on this side, the system on module and the evaluation board as a whole. It has an SPI interface. It's roughly 2 by 2 centimeters. It produces, at all times, I would say more than 10 megabits per second. It depends on the availability of entropy within your system, but typically we get values between 15 and 20 megabits per second, both for the hashed entropy data, but also the certification data that informs the entropy in your system. And yeah, as I said, there's an evaluation board available that you can just connect to your laptop via USB. And you've seen Clifford demonstrate this specific device. Looking at the timeline, so we've had, so PIC here just stands for Photonic Integrated Circuit, which was the black chip on the top right. We have tested and packaged that end of last year. We had our system module assembled beginning of this year. We did some evaluations and tests before the summer, and we've actually now shipped the second batch of devices just before this demo day. We will have 75 more units available after Q1 of next year. We'll then shortly after receive 2 more wafers that have already been commissioned, which means that by, well, let's say in roughly 1 year, we'll be able to go into production with this evaluation board and the system on module. Shortly after, we'll do a similar program that we've done for Vertex, which is the entropy source validation, which many end users care about. So we will be starting this as soon as the design is frozen, and we are able to get some data from it to evaluate it. But instantaneous knowledge of the randomness is not just important for cryptography. It is also very important for, as we've heard in the talk earlier, for stochastic computation. And one could argue that it is actually as important for this use case as well. Now, let me quickly introduce probabilistic computing. The 3 short teasers. Firstly, well, I'm just going to say who found it relevant to talk about it. Richard Feynman said you need to have very good random numbers from quantum sources in 1981 in order to simulate physical processes. Geoffrey Hinton kind of created this concept of restricted Boltzmann machines or Boltzmann machines, which have very significant applications in AI, and they are essentially nodes that have some stochastic nature included in them. And finally, as the work with Hartree Center has shown, it is fundamental to simulation codes like based on Monte Carlo methods and others. Just introducing the problem as a toy problem. Imagine you have a grid of values, and those values can only have two specific values, which is either 0, 1, or up or down, or whatever you want to call it. And if I look at a specific subset, for illustration purposes, I now look at how they interact with each other. So I can assign a value. If the nearest neighbors, for example, are the same, I'll put a 1. If they're not the same or the opposite, I'll put a -1. So this is kind of how I will be able to phrase a problem or describe a problem in mathematical form. And now if I change one specific of these values, and I pick that randomly or according to some schedule, I will change the effect that this interaction matrix has on this specific value. So that means I will get a different solution. And with a specific probability, if I'm able to change the bias of my probabilistic bit, which I'll introduce in a moment, or the random number generator, I'll be able to converge to a specific solution, which is in combinatorial optimization, the lowest energy state. Now, this was a 2D grid. This can have many, many dimensions. It can be a multi-dimensional problem. It can be very complex. And generally speaking, a probabilistic computing architecture models a stochastic physical system by mapping a problem to a physical system. So that's quite important. So the connections represent something. And the probabilistic bits, which are the units, essentially in this case, the quantum random number generators, that have a specific feature, which is that they are biasable. So I can tell them, give me a value between 0 and 1 with the probability of the bias at 0.6. So with 60%, it will be 0, but with 40% probability, it will be 1. And being able to change that bias in the hardware is quite essential for probabilistic computing. Just to try not to confuse anybody, so these are neither classical bits nor qubits. So they are defined by the property that they are biasable and that they randomly fluctuate in each iteration that I request a data set from them. They are based on exactly the same architecture as our other quantum random number generators for cryptographic purposes, because they require actually exactly the same features, fundamentally speaking. The architecture is based on these hardware p-bits, an energy calculator which evaluates at every point in time whether the random number is able to influence it positively or negatively to converge to a specific solution. And finally, the application of a bias to this probabilistic bit. So I'm not sure if you can see it, but I've drawn lines where I cover 10%, 20%, 30%, and 40% of that function. If randomly, my random number generator puts out the black line, then in the cases red and yellow, I will get a 1. But in the other two cases, I will get a 0, because the bias has changed. Why do we use photonics for it? First of all, it's massively scalable at room temperature. And secondly, it has very low error rates, because it doesn't really interfere with anything on our board. Now, when you put a qubit next to a qubit, and you try to entangle them, it becomes exponentially hard to scale your system. And people have struggled with that and are still struggling with getting high fidelity gates with that. In our case, that's not the case. It's linearly more difficult to, you just add another one, and because of the disk protocol, we don't have any error propagation. We exactly know how close or far we are from the theoretically predicted distribution. And that helps a lot with building a probabilistic computer, which you've seen outside. So this is the prototype that Max had shown. It will be deployed as a cloud service, as a remote service. It has Ethernet connection. It will just fit in any normal server rack. There is no specific environmental restrictions on that. You don't have to operate it in a specific way. You just put it there and it will run. And I think that's very powerful, especially when we look at the applications of this thing. So before going to the actual application, I just quickly want to talk about the mathematical problems that can be solved by such a machine, which on the one hand are QUBO problems. So this is what quantum annealers have been trying to solve, or other types of quantum computers as well. It's a specific mathematical description of a problem that has only quadratic terms in the energy function. I'm not going to go into the details here, but some representative problems are the max cut or the graph coloring problem. There are some applications in energy-based machine learning. Some interesting papers have come out over the last couple of years that show that probabilistic computing has a very advantageous impact on these kind of models. And there's arguments why they will outperform any type of LLM in the foreseeable future. And then finally, hypergraph optimization. So I said we are not restricted to quadratic terms. You can go much higher in dimensions, and you can actually leverage the physical nature of the system more efficiently if you do that. Let's go to applications. We've seen some of them earlier. So I'm going to jump over these ones quite quickly, because you've already seen them. So AI, ML, as I just mentioned. In simulations, you can actually simulate quantum processes better than a classical simulator can do right now, before needing to have the hardware for quantum computers ready. So you can now compute quantum problems with a probabilistic computer, and actually there's many papers that argue that a quantum annealer is only performing well because of the randomness, or the quantum randomness within the quantum annealer. There's no advantage of having an entangled system, and this is exactly what we are trying to leverage with our probabilistic computer. Finally, combinatorial optimization. In telecommunications, you can look at subband allocation in 5G networks. In logistics, you can have train and birth problem. There's many uncountable problems that can be optimized. Without going into details, but we can talk maybe a bit later if you're interested in some of the more bizarre things that people looking to optimize in big companies. Actually, finally, this is quite an interesting one, integer factorization. We talked about it previously. We have some results, not on the integer factorization problem per se, but looking at post-quantum cryptography, which is based on lattices. I'm just going to quickly go to results. In lattice-based factoring, you are trying to find a vector that points towards a specific point that you don't know previously, roughly speaking. And there's different phases within those algorithms that perform well on lattice-based cryptographic problems. And something that we've published last week, which are simulator results that have only come out 2 weeks ago, are showing that we can perform better by a factor of 100 in terms of the number of closest vector problem instances that you require to solve versus the best classical algorithm. And if you look at quantum algorithms like QAOA or Schnorr's algorithm, it's like a factor of 1,000 or 10,000, which sometimes they don't even get to this bit length. We are now, our simulator is run on 70 bits, so we're very far from having any relevance for encryption. But we've shown a very fundamental speed up over the best-in-class algorithms that try to solve this specific sieving phase in your algorithm. So I think this just shows that you can do a lot with a probabilistic computer that you cannot do with a quantum computer at this given point in time. Something that we published this week, actually, I think day before yesterday, is, I think, even more exciting, which are results that show that for problems that are very difficult to run with quantum computers, but also with the kind of the replacement that people currently use, which are tensor networks, we can show that we can solve an arbitrary complex problem just by scaling the size of the probabilistic computer. So here we have an inflection point, and past this inflection point, we don't need more operations or iterations to solve a problem. We just need more p-bits. And given that it's very easy for us to scale the number of p-bits, currently we are at, in this prototype that you've seen, it has 64,000 logical p-bits. The simulator went up to 1,000. So we can go to very, very high precision solutions to solve what is called bi-clique problems, which has strong implications for applications in neural networks. So we can run very, very big neural networks, and we can solve them very efficiently, and we'll be able to beat, even with this prototype, for example, a D-Wave Advantage 2 system very easily. Application of this is fraud detection. I think we heard about this earlier today. Portfolio optimization, customer segmentation, etc., etc. So this is a max cut and a Ricard-Boltzmann machine problem. Upcoming, there's two exciting things that we'll be publishing soon. One is about the minimum hitting set, which has applications, for example, in drone fleet management, and the traveling salesman problem, which I think is self-explanatory. If you look at, I I think there was a mention of Ocado today. There is, there's a problem that can be framed to arbitrary complexity where you want to optimize a route, essentially. And the traveling salesman problem is one of these problems, and we are benchmarking this against GPUs to show the advantage of our system. Finally, the next steps that we've planned. So we are integrating all of the algorithms currently into our hardware prototype. So some of the simulator results will be replicated, and we will not just know the number of iterations that are needed to converge to a solution, but actually the time to the solution. In December, we'll publish some of the hardware results just to make sure that we inform everyone that has been working with us on the project about the advantage that the prototype already can bring or can deliver to their use cases. We'll also release a simulator, so everybody will be able to get access to those algorithms, because there's quite a few that we have developed and quite a few that we think are best in class. And finally, starting from February, we'll be giving remote access to the hardware, and it's actually to an updated version to what you've seen today, which is going to be performing even better. So the physical p-bits will be smaller, they will be more performant, and we'll be able to integrate them more tightly within the existing system. This is everything for the tech update from my side. Thank you very much. I hope you will have understood why we're going for these very different fields of cryptography, but and also probabilistic computing, because it's all based on exactly the same technology. The two features that are key, and that Quantum Dice has really pioneered, I think, find applications in both these use cases, and that's why we think it's very important for us to work on both of them. So thank you very much for your attention. If you have any questions, feel free to either catch me after or ask them now.